understandings about what. Thank you for calling. Okay, so I'll just dive straight in. So let's start right at the beginning, which is this idea of MLP. What is MLP? What is multi-layer perceptrons? Let's start right from the idea of a neuron. The idea of a real human neuron or animal neuron or a biological neuron is you really do have nodes and edges. You have a node here, which is the dendrite, and then you have an axon, which is where information is passed. And the cool thing with this is you can get a chain of these, you can link them all together, and you can start storing information, training information, you can start inferring, and the exciting thing is you can start learning. That's what neurons allow to happen. So this was obviously kind of moved into the computational realm where people not necessarily try to replicate it, but realize that you could treat information using kind of virtual neurons. And that is what MLP really tries to do. So you have a bunch of inputs, which might be represented as nodes. And then you would have some kind of edge, which allows you to pass information generally through a weight to a different node. And these would be passed along in a chain through hidden layers until you get to some output. I know this is the simple background, but there's a reason we want to build from simple and go to complex, because cans are about to destroy all this, which is the exciting thing. So let's keep going here. So let's take, you have some kind of neural network, which is trying to figure out if an image is a cat or not. This is a very simple example. Now let's say that it identifies a bunch of features. Now these features might be things like, can the neural network identify a fluffy tail in the picture? It might be, does it have pointy ears, or maybe a paw shape, maybe the cat's face, or maybe a different angle. From paws aren't always going to be facing the same direction. So these are identified as very important things to identify if it's a cat or not. Now we have a bit of a problem, because as soon as you introduce a dog, you might see many of the same features. You might see that there is still a fluffy tail. Therefore, according to this neuron here, this is valid. It could be a cat. You still have pointy ears. They're slightly different, but they're pointy ears, and you have similar paws. So this is where you get the idea of activation functions. Activation functions really work as kind of a nice filter to understand what's important and what's not important. The reason being that a fluffy tail might be important for understanding if it is, in the realm of being a cat, rather than being a lemon, for instance. A lemon wouldn't pass this test, but a dog and a cat would. But then you see that actually the cat's face is far more important. That's more identifiable and is used in many cases. And so that becomes more important. And activation layers really allow us to understand the importance there. So they work generally by trying to add some kind of filter of trying to map a value to its importance. Therefore, for instance, you may have a value of -6 coming in. That would get mapped to a value of 0 with this particular activation function, meaning it's not very important. Likewise, maybe you've got an input value of 4 that's getting mapped to a value of 1. Therefore, it is quite an important neuron. And that's what activation layers really allow us to do, is to filter out what's important, to start to scale these and to understand what's useful. So they're a vital part of the neural network. So this is how it's generally represented in MLP, is you have generally a bunch of features, you have a bunch of activation functions, some degree of layers, hidden layers, and then you have an output. Now, I'm now going to change tracks completely, so save this to your short-term memory, and then we're going to link these up later on, because the next thing I want to talk to you is a little bit about Kolmogorov himself and Arnold. So Kolmogorov is a brilliant mathematician, arguably one of the most important mathematicians of the 20th century. You've probably come across some of his work in statistics, and he had a student named Arnold. Arnold is a Ukrainian mathematician who worked with Kolmogorov to identify solutions to what's called Hilbert's 13th problem. So Hilbert was this really nerdy maths dude who figured out a bunch of problems that were unsolved in mathematics. And his idea was that if you can solve these problems, then maths in general can progress, and the world can be benefited by solving these problems. And Kolmogorov and Arnold were able to solve the 13th problem, which started to identify how you can simplify mathematical functions. So let's take the Kolmogorov-Arnold representation theorem and apply the idea to something like a painting. So this is a Monet painting, and what you can see is it's pretty complex. So if I was to try and give you instructions to try and tell you to replicate this painting, how to make this painting, I'd have to give you quite detailed and thorough instructions. So I might have to say, you've got a field of poppies, which are kind of fairly impressionist. You've got 2 figures in that field. You've got trees, which are blue and green in splodges with these kind of dark trunks. You've got a whitewashed sky, and then this blue horizon in the background. Now, what I'm telling you there is fairly complex instructions, and yet I guarantee what you would paint, having not seen this painting, would be totally different. It would be quite a poor representation. So let's zoom in a bit. Let's try and simplify this. Let's take a smaller section. Now it's going to get a bit easier because I can say, okay, there are 4 trees, which are vertical paint strokes. Then you've got some splodges that represent leaves. You've got red and yellow splodges that are flowers, and then figures in the foreground. So that's a bit easier. Now let's simplify this even further. Let's go right all the way in. Now we can actually get very, very simple, simple sets of instructions. We could say, for instance, on this coordinate, put a splodge of paint and make it this color. And then you move to a different coordinate, put a splodge of paint and make it this color, and so on and so on and so on. So you see we're simplifying each time we go. So what you could really do is break down this whole painting into a series of very, very simple instructions. Wait for the motorbike, sorry. So you can paint these into very simple instructions. So what Kolmogorov and Arnold were able to do is show that the same can be said for any single mathematical function. The idea is that any mathematical function can be broken into an additive sum of other simpler equations. So this is represented here. You can have any number of inputs, any number of parameters, and it can be broken down into a simplified equation. Let's take a real example of this, of how this might work. Say we've got a simple function here, which is sine of x multiplied by cos of y plus x squared plus y squared. Now, this isn't hugely complex, but there is actually one complex element in here, which is the sine multiplied by cos. That's not actually a simple function to work with, but Kolmogorov showed that actually you can simplify this. So let's take only a sine function, only a cos function, and 2 squared functions. And these are the representative planes from those functions. And actually, if you sum those all together, you get the equivalent of the original function. They're exactly the same between the two. And what Kolmogorov and Arnold were able to show is that actually any complex function could be represented by a series of simpler additive functions. So this is really, really cool. So how does it apply to MLP? What's actually the use here? So this is from the paper, and I do encourage you to go and read the paper. It's very accessible and it's really cool. But let's just focus on the CAN side of things. So what we're able to see here is that as opposed to a normal neural network or any kind of MLP, we actually have activation functions on the edges. So every edge here has an independent activation function, which can be learnt. Similarly, you have nodes still, but these nodes operate as sum functions. So you sum any neuron coming into here, any activation function, and you get a result out of that. This can operate in a deep model. So for instance, this, where you have a number of hidden layers with activation functions and some nodes. This is different to traditional MLP, where traditionally you would have the activation function is fixed, it's set, and that happens on the nodes, and then you have weights on the edges. So we really flip the problem on the head here, and actually we have a completely different understanding of how we're learning within these models, which is pretty exciting. So what does this actually allow us to do? And this is where I hope you see that what the benefits are. Let's say we're trying to represent a more complex function, which is e to the sine of pi x plus y squared. Now, if we don't give the model this equation, we're just going to give the model the inputs and the expected output from this function. And we start to train on that. What we can see is after step 20, it started to fit these splines. By the way, the current implementation only uses splines to try and understand what are the functions that we need to add together in order to get to this output. And this continues until you get to step 100, and I've got a zoom bar in the way, so I can't actually see. But sorry, it's not too noisy, is it? Because I can move. We're still good? Okay, thank you. Okay, so what you see is at the end, after we've pruned everything, suddenly we've got a representation that is trying to replicate this function here. Now, can you see what's happening here? This is actually really awesome. You've got the y goes into what is clearly a squared function, so that's y squared, which is over here. You've got the x, which is clearly going into a sine function, which is the sine, and both of these are summed within an exponential function, which is sine e to the sine of pi x plus y squared. So actually, we've actually perfectly replicated this function by building this kind of model. And this is maybe the most important aspect of CAN, is the explainability aspects. It's very, very easy to understand the actual functions that are being developed by these models. It's not just a bunch of weights multiplied by very difficult to understand activation functions. They're actually very, very extremely explainable. This is cool. So this is how it looks in action. So you can see that actually you can get quite complex outputs. But the point is, at any point you could pause here and actually see what the exact functions that are going into these nodes here. Very, very cool. So how does it work? Let's look at some examples that the paper ran with some complex functions. Here's the one we just looked at. Here are some more complex ones down here. And what we have in the colors is MLP examples. So you have depth 2, 3, and 4, and 5 are these kind of colored functions here. And here's how they perform. So they're pretty good root mean squared error with a high number of parameters. But if you look at a CAN, it blows them away. It has nothing even close. Within just, only with 100 parameters here, it's far outperforming anything else by orders of magnitude. And this is generally the case for simple equations. It's the case for complex equations. And generally, you don't see the same plateaus that you do with some of the deep learning aspects implemented here. Perhaps it's more demonstrative on PDEs, potential differential equations, where we see that actually it kind of blows everything else out of the water. You've got, if you have an MLP example, we've got an architecture here, which is 3 layers or 3 hidden layers, each with 100 nodes. And what you can see is it does pretty well. It goes down to an L2 squared error of 10 to the negative 4. That's pretty awesome. If you do a CAN implementation, it goes a bit better. But let's have a look at that architecture there. It's only got a single hidden layer. It's not 3, it's a single hidden layer with 10 nodes. So it far outperforms the deep learning, sorry, the MLP method. If we look at the MLP method with the same architecture, 2, 10 of 1, then you see that it basically does nothing. It does a little bit 1 on H1, but very, very poor. So this is the exciting thing, really, that actually with much fewer steps, we can get to a higher degree of accuracy, and yet with a simpler architecture. So this is what's exciting for the future. So why is that useful? Well, let's look at the evolution of parameters over the years in order to get to these large language models here. GPT-4 at the top here, obviously, uses many parameters, it's insane number of parameters, and that is only growing. So the idea is if you can now get the same outputs using a CAN with much fewer parameters, suddenly this GPT model can drop down orders of magnitude down to here. It's suddenly much easier to train such a model. What that really means is hopefully it's easier, but also you could just even use more parameters, bring GPT back up to its complexity, but you've got way more parameters here, which is really exciting. What's really cool, additionally, is the explainability, as I mentioned previously. Because you can look inside and actually understand these models. Please stop me if it's getting too noisy. There's lots of people coming around me. Because these are so explainable, you can really understand things like bias within models. So here is a bunch of GPT models, a bunch of large language models, and they all have inherent bias within them. And that's very hard to understand that. Is it due to training data? Quite often not. Literature says that actually that's not necessarily the driving factor. It's a factor, but it's not the factor. So why does an LLM make a certain decision? Why are these decisions being made? And that's what CANs are really hopefully going to open the door for, is looking into these models and understanding why decisions were made, which is really super exciting. This is perhaps the main reason for CANs. The original paper was published by a physicist. It's not an ML expert. They are a physicist who's very good at ML. And the reason they're interested in their research is they're looking at how can CANs be applied to discover new physics. So here are the Feynman equations. So Feynman had a list of kind of equations that were fundamental to physics, why they were important. And basically they trained the CAN on all of these and were able to replicate all of the equations that were present in Feynman's equations. So this is really exciting. It really shows that you can at least understand physics using these very explainably. Think about for things like fluid dynamics, where it's almost impossible to actually generate the equations because they're so complex. What you could do is essentially train your model on the data, the labeled data, and it's going to show you the functions and the equations that build the output. And that's just fantastic. That shows why the explainability is maybe the most exciting bit, especially for physicists. Let's also focus on the actual compute time. What we can see is that over time, you need increasing compute time in order to train these models, but that is flattening it out, somewhat to do with efficiency, but also because Moore's law is dead. It has been dead for 40 years. So this is why GPT is really going to struggle to get to the next step. However, what CANs are really offering is a way to reduce the current compute time for a lot of these and hopefully bring up that curve again as we can train much more complex models with equivalent training times, which is really fantastic. So let's try it. I tried it on some of my data. Now, The thing is, everything we see in the paper is very, very clean physics. It's equations that we all know and understand. They're solved. But let's try it on something messy. So I had a data set I've used previously, which I couldn't really do anything with because it was too messy. It was very, very noisy. There's very limited signal that you can actually use for predictive purposes. So it's just a binary feature to predict, and it's very, very it's evenly sampled as we see here. So let's run it on a CAN. To use a baseline, I have a very simple neural network here. Architecture is simple. It's 2 layers, 128 and 64. And it got to an accuracy of around 65%. That's better than 50%, which we'd expect for balanced binary random chance. But actually 65% is about as good as I'd expect with this one. As I say, it's pretty messy data. So the first attempt with just a neural network, just a simple one layer with 16 nodes, heavy overfitting. So let's put some dropout in, and we can see we can get to an accuracy of 64.5%. So we've lost about 0.5% of accuracy with a simpler model. So you know it's doing okay. It's doing its best, but it's a bit messy. Let's try the same with a CAN. You see again massive overfitting. We're going to add some dropout in there as well. And we see we're back up to 65%. So same architecture here with 16 hidden, with one layer there with 16 nodes, and we're back up to 65%. So this is the point I want to make, because hopefully this is a bit disappointing. It's not a magic fix. So a lot of the hype you've seen on the internet probably has been talking about how this is going to revolutionize data, because people are expecting this to be a magic implementation that suddenly terrible data becomes usable data because CANs can do all this amazing stuff. The truth is, it's not going to make any difference to quality. What it is going to make differences to is things like efficiency and training times. Which is exciting, but let's not overhype this. Also, arguably, what I just showed you was the wrong use case. As they say in the paper, this is meant for physics. It's really meant for where there is a solution, a solid solution. It's just that solution is hard to find. It's difficult. So it's not necessarily for noisy data. It's for much, much simpler data. Here's a resource page. I really encourage you to go and have a look at. Let's open it up. This is Awesome CAN. It's a repo where they've just started collecting resources about CANs. Here's the original paper. Please read it. It's fantastic. And here is the original library. Having said that, there is maybe a better one that's now come about. As I say, this was written by a physicist, so it's in pure Python. But there's a torch implementation you can find at Efficient CAN. That's what I was running on. There's already a ton of different implementations, faster CAN, fast CAN. And then there's all sorts of ways that people are playing with this. As I said, everything at the moment is done through splines, but people are looking at all kind of different ways that you can add different polynomials, there's a Fourier one here. Which is really exciting. Jacobians, I think, is maybe one of the most exciting ones. I didn't get to play with that yet, nor have I got to play with the graph neural network version, but I will be doing that very, very soon. It's pretty cool. There's tons of convolutional versions of this as well. There are language model ones. There's people are playing with this a lot. There's a lot of stuff coming about. There's also good tutorials on this page and kind of just descriptions of how you can simplify this, and people describe it way, way better than I ever can. So I encourage you to go and take a look. I see I went through that way faster than I intended to, sorry, but hopefully that was a decent view of CANs, and I'd be happy to talk about this with anyone or answer any questions.
Oh, I immediately, I hate to jump in. I'm going to be, oh, Arnaud has his hand up. Crap. All right. Arnaud, you can go first, and then I have questions.
Okay. Thanks for the presentation. I was wondering, how are these learnable activation functions represented?
Oh, okay.
So currently they're all through splines. So you give some kind of order of complexity for the spline, and then it will try and fit that. But generally, you can then simplify them. So they have an option for you to tie them to functions. So they have a list of simple functions: sine, cos, exponential, squared functions, all of these. So you can then tie the splines to the nearest function that fits that. Quite often they're complex polynomials, but if you have simple cases, you can definitely, as I showed, get like the squared functions and the exponential functions, which really helps.
Okay.
So my question, and I hope this isn't too into the weeds. So the way that I tune my weights on a neural network is that I'm taking the loss function, and then I'm using calculus to go back through the nodes and take a step in the direction of the greatest descent. Like gradient descent is the most simple. How are they, what is the process that is being used to fit the equations?
It's very similar. It's still backpropagation at the end of the day. The only real difference is the learning is on those activation functions rather than on weights. But at the end of the day, they're still experimenting by changing those functions and seeing, you know, what gives the optimal gradient descent from that.
Okay. Yeah, I guess it just feels like it would be more complicated because just the difference between a polynomial and a sine function is not like easily represented as like a gradient in my mind. So it's I really want to dig into it, but it seems more like it would be more complicated. Anybody else questions?
Tom, can I have a question?
Yeah, go ahead, Jan.
Yeah, I'm wondering, did you read something on why this is a thing now? Because it seems like there was nothing preventing learning activation functions before, right? So why did we focus on the weights before so heavily?
It's pretty funny because there's kind of a disclaimer at the repo from the original paper where the original author is basically clearly overwhelmed with this. Like suddenly there's been so much attention on it, and I think it's because it's not necessarily it wasn't a big leap. You know, as you say, we've known about this kind of mathematics and things for a long time, and there are some papers from 2016 that explore the idea of it, but don't really look at implementation. But just I think it's one of those things that nobody thought of trying it. You know, and this poor guy tried it and has had extremely way more success than he ever imagined he would. So he's getting questions from all over the world at the moment. So I really think it's not like a big leap in understanding. It's just that nobody thought to try it.
Yeah, that's amazing.
How many layers can you have of that? Like, do cans also work well with very deep networks?
So the funny thing is, it's hard to find something complex enough where you need deep architecture because cans are very good at working with a few nodes. So I found that I could do the same as what I just showed you. I had 16 nodes there in one layer. I could do the same with 4 nodes. It was giving the same result. I just wanted to be demonstrative. So as soon as you add another layer, you're not really gaining much. Maybe for some of these extremely complex equations, you can build deep layers, but their point was actually the instructions are start as simple as you possibly can and then build up because actually it's extremely easy to overfit with these networks.
Mm-hmm. And maybe you've answered it to Mal as well, but like I'm still struggling to understand how. So do cans use backpropagation?
Yeah,
as well. Yeah. How like and then you said that activation functions are represented by splines.
Mm-hmm.
Does it like how does it kind of move those like the points in the spline or like through backpropagation? Like how, if you could explain a bit more on that.
My knowledge on
How it
splines
works.
is terrible, but they do have a whole section on the paper where they describe exactly that, how they're actually optimizing for. And this is why they're using splines, because there's some functions that work well for splines that they were struggling to reproduce with other things like polynomials, but other people have managed to have implementations of those kind of things. So I'm not going to answer because I'll get it wrong. So please do go to the
Okay,
paper.
yeah, I'll do my
But
research.
it's
Thank
still
you.
basically the same concepts of kind of backpropagation, figure out which way is going to give you a better descent, and then yeah.
It's super interesting to me, especially because I feel like when I was at Berkeley, I remembered some professor making an offhanded comment that theoretically any 2-layer neural network can represent any complex equation if you give it enough nodes, like if you make it wide enough. But this seems like it's literally they have it's more, it's not theoretical. It's like we've proven mathematically that we can represent equations using this method of breaking things apart. So this is super interesting.
Definitely, yeah.
Do you have any thoughts on the explainability? I see how it works for physics because it reduces down to the functions you see you can study, right? But do you see how explainability could work for in other domains?
Yeah, I mean, if you have extremely complex networks, they're still going to be hard to explain. Let's be honest. But I guess it works in 2 ways. One is that those extremely complex networks are now simpler. So it's easier to dig into them physically. But also, yeah, because you know the exact activation functions on each of them, you can start to break down, if you can start to figure out what routes are specifically around, certain features in your data and why it's using those, why it's feeding that through that route. So I think that's the explainability aspect. And actually the author's implementation, it's very kind of rough, but it's really fun to play with because they, as I say, they allow you to tie to simple equations. So you can take what appears to be a quite complex network and it'll just print out the formula for you, and it's way simpler to see like that. So it's really fun to play with.
I want to give an opportunity for the people that are sitting in the room downstairs, if you guys want to jump in and have any questions you'd like to ask. If you guys are saying anything, I think you might be on mute, but.
You can repeat it for that.
No questions, but very, very, very good presentation, Tom. Thank you.
It was very interesting.
Pleasure. Yeah, sorry if there was background noise. As I say, it was I picked a bad spot, but it was
It was surprisingly clear.
okay.
Yeah.
Cool.
Yeah.
If there's nothing else, I'm gonna go back and get some more pick and mix from that bar.
Yeah.
And then,
Cool. Thanks for taking the time to jump out. Tom, who do you want to nominate to jump on the end of the list?
oh, power! I like this. I think we have a few people on the list, but no, I feel bad. I think if someone's got something great, they should share it. But I'm not gonna pick anyone.
All right, I will only let you get away with this because I think we already have 3 people on the list. But going forward, you have to nominate somebody when you share. But thank you. I really appreciate you taking the time out of your out of this convention to come share this with us, Tom. We've been looking forward to it for weeks. So cool.
Great fun. Thanks, everyone.
All right, thanks, guys.
Thank you. Bye.
Bye.